Thank you. Well, before my talk, let me advertise one thing. We, RIKEN data assimilation team will hold an international school on data assimilation on this January, in which Greg will join as a lecturer. So if you are interested in this, please come visit us and check this webpage. Okay, let me start my presentation. My talk is about isotopic proxy data assimilation, and my collaborator is Kei Yoshimura and Takemasa Miyoshi. And my talk is very similar to Nathan's one and also David's one. So I'm not sure I can add something new, but hope you can enjoy my talk. And my talk is based on this paper published in this year. So I totally omit the background and I want to jump to the methodology. The slide shows the models I used. The models consist of 1 AGCM and 3 isotopic proxy models or observation operators. My atmospheric model is isotope-enabled MIROC5, and I used 3 isotopic models. One is Coral model that is developed by Thompson et al. 2011, and also by Liu et al. 2013. In my model, isotopic ratio in Coral is linearly combined with isotope ratio in seawater and SST. And for isotope ratio in tree cellulose, I use Rodin's model. And I'm using monthly data to calculate monthly isotope ratio in cellulose. And then after that, I averaged it to calculate ion mean by weighting NPP, net primary production. And for isotope ratio in I-score, I developed one model, but it was kind of garbage, and I decided not to use this. I simply average O18 in precipitation by precipitation amount, weighting by precipitation amount. So to assimilate proxy data directly, the reproducibility of models is essential, right? So first, I would like to show the reproducibility of my models. This slide shows the isotope ratio in precipitation simulated by my model and observed by GNIP. And as you can see, those well-known isotopic patterns are well simulated by my model. And then if I compare my model reproducibility with the other isotope-enabled models, swing 2 models in Taylor diagram, the result is plotted like this. So as you know, this is Taylor diagram. So if the model is plotted close to here, which means that model reproduce well, and my model is here and here for annual mean and the seasonality difference. And that means that my model is totally normal compared to the other models, and nothing superior to the other models, but it's good for me. But when you see the internal variability, reproducibility of isotope ratio of internal variability, my simulation, my model did a little bit well. So top panel shows the correlation between observation and nudged simulation for temperature, precipitation, and isotope ratio in precipitation. And then if I count the number of sites which are statistically well correlated, the number of correlated sites are relatively larger than the other models like GIS or GSM developed by Gavin Schmidt or Kei Yoshimura. So how about the reproducibility for isotope ratio in proxies? This map shows the mark shows the proxy types. Triangle is for true cellulose, and diamond is for coral, and circle is for I-score. And if the model reproduces the proxies well, that is marked as red. If not, it's marked as black. And I plot this map for the period of last century. And to summarize this figure, this map shows the result. So this bar graph shows the percentage of proxies that are well reproduced by my models. And as you can see, this is for precipitation, isotope operation in precipitation, and isotope operation in ice core, coral, and touring cellulose. So except for ice cores, the models do pretty well, and at least the skill is comparable with precipitation ratio, isotope pressure. So I don't know whether this is good enough or not, but anyway, I used this model to assimilate isotopic proxy data. So this figure shows the flowchart of proxy data assimilation and my experimental design. First, I did OSSE for the period of 1871 to 2007, and I used the stationary offline data assimilation, which is proposed by Steger et al. 2014. And I did a 1-year assimilation cycle, and I didn't do any monthly reconstruction. So my state vector include annual mean temperature, precipitation, and isotope operation in coral, touring cellulose, and ice cores. And so the first case is simulated climatology. And the background error covariance is constructed from the long-run simulation. And in the control experiment, I assimilated isotope ratio in proxies, and then I set the error of 2.0 in the scale of signal to noise ratio. And I assimilated 94 proxies plotted in this map. So this is the result. This figure shows the correlation between truth run, nature run, and the reconstructed run, and for temperature and precipitation. And the green dot shows the observation site, and hatched area shows not significant area. And I think this map is quite similar to the other guy's figure. And I compared with the other assimilation case. In the other assimilation case, I assimilated temperature with noise. And this figure shows the difference between DA assimilated isotopic proxy and DA assimilated that temperature. So if the map is red, which means that proxy DA is better, and blue means reconstructed DA is better. And if you averaged all globally, the delta R is 0.1 for temperature, and delta R is 0.12 for precipitation, which means that isotopic proxy data is comparable with reconstructed temperature data assimilation case. So, encouraged by this result, I assimilated real proxy data. To remind you, in the previous case, I did OSSE, so nature run is created by myself. But in this case, I assimilated observed proxies. And I named that next experiment name as real. In this case, I used to construct background ensemble by using CMIP5 SSD to drive AGCM. And okay, let me skip this. And if you want to assimilate real proxy data, there always exist bias, as the other people pointed out. So I first normalized data, and then I super-opt the data, which means that I regridded observation data to fit the atmospheric model grid. Okay, so this is the result. Again, this is the correlation between the analysis and, in this case, observations. Observations are HAD-CLUT for temperature and GHCN for precipitation. And if you compare with the control case, that is OSSE, as you can see, the result is degraded as expected. So I want to explain what degraded the scale. So I did additional 2 experiments. I already showed the result of control and real, and control is idealistic experimental setting, and the real is realistic experiment. And I added 2 experiments. That is, one is CZCM, in which I changed the SST data to drive AGCM. And so in this case, nature run, in this case is still OSSE, but the SST to run to create nature run and background ensemble is different. And VOBs, in this case, I additionally changed the number of proxies to fit the realistic case. Okay, so this is the result again, and I used again the correlation coefficient, and the bar shows the globally averaged correlation coefficient for temperature, precipitation, and I additionally brought Nino 3 in this figure. So the difference between control and CZCM is represents imperfect SST, and the difference between CZCM and VOBs explains the degradation explained by number of observations, and this one is explained by model error and mismatch between observation and simulation. So this is the conclusion. Well, as I showed in this figure, gaps between control and real remained unexplained, and that includes model errors and biases and observation error correlation, such kind of things. So in my experimental design, I couldn't explain those errors, so I need to keep working on this. And as for the control case, still there are lots of unanalyzed area reminded due to the paucity of observation data and short correlation length. So we need more observation, and also we need to create better first guess. To do that, I think we need to move on to online DEA. So that's it. Thank you very much.